Okay, in this last presentation I'm going to go ahead and show you how to modify the data in order to make sure whatever function you produce is a linear function. So again, our 4 steps: we need to identify the variables, write the equation in terms of y equals mx plus b, and now we're going to alter the data as needed, determine the meaning of the y-intercept, and determine the meaning of the slope. So let's go with this experiment here, which will not produce a linear function for us. A student wishes to determine the acceleration due to gravity. He takes a ball and drops it from various heights. He uses a photo gate to determine how long it takes for the ball to fall from each height, so that we can get more accurate data. How will he use his data to determine the acceleration due to gravity? So the physics equation we would want to use would be our free fall equation. We can go ahead and move the x naught over here, so that way we get a change in position, also known as height. The initial velocity, if he drops it from s, is 0, so this term disappears. That leaves us with a 1/2 at squared. So delta x, as I said before, is height. We get height equals 1/2 at squared. The steps: our independent variable is height. The student is controlling that as he pleases. Then the height determines the time it will take to fall, so time is the dependent variable. When we rewrite the equation, we need the dependent variable to be on the left, so we'll have to move the t squared on the left side, and we'll have to move the h onto the right. What I could do is I could just go ahead and take this equation, rewrite it as 1/2 at squared equals h, multiply both sides by 2, and then divide each side by a. Now we get t squared equals 2h over a. There is no y-intercept in this equation, and our slope is 2a, or I'm sorry, 2 divided by a. A is our acceleration due to gravity. Here's the issue with this. This is the data set produced for the lab. And once we graphed it, this is our resulting graph. You'll see this graph is not linear. Therefore, we can't do a y-intercept and slope analysis. This is going to occur because as we take our equation and modify it, get down to the final equation here, h equals 1/2 at squared, we see it's a function that depends on t squared and not t. Our original graph, t, is going to produce a square root function. So what we want to do is we want to take the data and modify it. There's a simple solution. We're going to graph the variables as their exponents instead of just the variable itself. Since the equation calls for t squared, we're going to take all the data under t and we're going to square it. So let me step out of this really quick and go into Excel. We see the data set here and our graph here that produce a square root function. We're going to modify it. So what you would have to do on an actual AP exam is you'd have to do it by hand. I have about 20 sets of data here, so I'm going to let Excel do it for me. I'm going to create a new column for my dependent variable. It's going to be time squared, measured in seconds squared. Whoops. Square this 2. There we go. I'll go ahead and set this one equal to the time squared. Now drag this all the way down. Make sure I got enough data points there. And now our data is set to go. This is the new data we want to use with this independent variable here. So we're going to click on the graph, select the data for the height and t squared, click OK, and now we have a set of data points that looks a little more linear. We can click on the data points, right click on one of the data points, click on add a trend line, Our trend line is going to be linear, and then we're done. Now we can take a look at this line. We can see what the y-intercept is, and we can calculate the slope. The y-intercept, as we said before, doesn't exist. There should be no y-intercept with this. That tells us if we drop it starting on the ground, it's going to take 0 seconds to hit the ground. That makes sense because it's already touching it. The slope of this line, and again, if I want to calculate it, I don't use any of these data points to determine the slope. I only use points on the line itself. But the slope of the line will be equal to 2 divided by a, where a is the acceleration due to gravity. So, let's try a few more examples to see how we can go ahead and linearize the data. Students switch to determine the acceleration due to gravity in another way. They're going to use a pendulum. It's going to swing back and forth. They're going to vary the length of the pendulum, and they'll record the time to complete a period. This is the equation of a pendulum down below. And that's the equation we need to modify. The independent variable is the length. The students are determining the length, which as a result is going to cause the period to change. That makes the period the dependent variable. Our equation is almost expressed the way we need it. I just did a quick modification. Instead of a simple algebra trick, I took that square root of g in the denominator and I put it underneath the 2 pi to leave the square root of L by itself. So what I have here is I have the slope and then my independent variable. We're going to need to modify the data because L is under a square root. So I'm going to take all the values for length and I would calculate their square roots. The equation shows me there's no y-intercept and that the slope of the graph that I produce will be 2 pi over the square root of g. So when I calculate the slope, I would set that equal to 2 pi over the square root of g, and I would solve for g. Again, the graph, on the x-axis we will have the square root of length, and on the y-axis we would have the period. Here's one more example. Astronomers wish to run an experiment that will calculate the mass of the Earth. They take data from satellites orbiting the Earth at various distances. The astronomers know the distance of the satellite from the center of the Earth. And what they do is they time how long it takes for those satellites to orbit the Earth. Then they use a derived equation, gmt squared equals 4 pi squared d cubed. G is a fundamental constant, m will be the mass of the Earth, t would be the period it takes to orbit the Earth, and d is the distance from the center of the Earth. The independent variable the astronomers chose was the distance from the center of the Earth, and that meant that the time it took for the satellite to orbit was dependent upon that, so the period, or the time it takes to orbit once, is a dependent variable. We have the equation gmt squared equals 4 pi squared d cubed. We're going to move the gm to the right side of the equation by dividing both sides by gm. And we produce the equation you see there. T squared equals 4 pi squared divided by gm, all of which is multiplied by d cubed. Our independent variable here, d, the data for it needs to be modified by cubing it. And our dependent variable here, the period, needs to be modified by squaring all of the data. There's no y-intercept produced for this graph. That makes sense. Physically, what it's trying to tell you is that if your satellite was sitting at the exact center of the Earth, it wouldn't take any time to orbit the Earth, because it wouldn't be orbiting. The slope of the graph will be 4 pi squared over gm. So once I determine what the slope is by graphing it and calculating it, I would say that that slope, whatever number I calculate, equals 4 times pi squared divided by gm, where g is the universal gravitational constant. So I know the value of that, and then I can solve for the mass of the Earth. The distance from the center of the Earth cubed will go on the x-axis, and the period squared will go on the y-axis.